Hello, here we are going to take a look at a couple small applications of exponential functions. First one, depreciation. So the depreciation of an object is often modeled by some type of exponential function, a sort of gradual one. Depreciation means how much value does some object lose over time. Cars are a great example of this. The value of a new car decreases as soon as it is driven off the dealer's lot. The function v is equal to 25,000 times 0.82t models the depreciation of the value of a new car that originally cost 25,000. What values of v and t are meaningful in the function? Alright, so we have an I on our function here. What's meaningful there? This is just a good exercise of some mathematical thinking. For v, things about v that I care about. This right here, notice that 25,000, that's also what the the problem said is the value of it originally. So I'd say 25,000, which is new cost. That's pretty important. And you see that appear in the function. Graphically, because on the right we have the graph, notice how our exponential function at t equals 0, the value of our car is 25,000. That's the y value of our curve. So even our graph shows that. T, what times are meaningful? Well, at t equals 0, the cost is 25,000. That's pretty meaningful. But notice this curve shows as it depreciates. So after 4 years, what is it? Approximately 12,000 there. At 8 years, we are about at 5,000. So I'd say a meaningful year here is when is the car basically worthless. Way down here at year 15, our curve is approaching year 0. There, the car is only worth maybe $500. And this curve is going to keep going. It's going to approach 0 but never cross it. It approaches that line right here. And we have seen that in our behavior of exponential functions and graphing them. So our graph doesn't extend very far, but it does go out to year 15. So I would say t equals 15 is pretty meaningful. 15 years means car is worthless. After about 15 years, there's no point in selling it or even trying to sell it. You might as well just drive it into the ground and just keep driving it until you have 500,000 miles on it, because at that point, it's not worth anything. Okay, so those are a couple meaningful things based on the graph and our function. What is the value of the car after 5 years? The easy way to do this, go to your graph at t equals 5. And what is the y value on our curve? It looks like approximately 10,000. So what is the value? 10,000. And that's the easy way to do it when you have the graph there. Now, of course, you could go and use the function because they give us the equation. And you go 25,000 times 0.82 to the 5th power because t equals 5. So you'd go 0.82 to the 5th in your calculator, multiply by 25,000, and you would get our estimated answer here, or approximately close to that. Because notice this right here would give the exact answer. We're using the exact function. This is just an estimate because we looked at the graph and it kind of told us that. Move on over, switch gears a little bit. Determine whether the set of data displays exponential behavior. Explain why or why not. Exponential behavior. What does it mean to be exponential? It means that you are growing at a rate that depends on how large you are. That means you're growing at a rate that is doubling in size, or tripling in size, or halving in size. You're getting half as big each set time. So exponential, you're like growing at a faster and faster rate. You have to look for as x increases in set amounts, so it's increasing by 10 each time here, as x increases in set amounts, y must increase by a multiple, by some factor. It must go by times 2 or times 3 or maybe times 1.5. So to check that, we are going to compare these y values to go from 10 to 25. Now, I don't know if it's multiplying or adding or what is it, so I think, okay, so I can add 15, or I can multiply by 2.5 to get there. I check the next one. 25 to 62.5. Well, that would be adding 37.5. So there, I notice that my adding is different. So already it's not following that pattern, so I can kind of knock that out of the game. What about multiplying? 25 times 2.5 is 62.5. Okay, what about the last one? Now you could check this in your calculator, but 62.5 times 2.5 is once again 156.25. So I see that to get to each of my next y values, I can just multiply by 2.5. So in each of my set intervals, as x increases by the set value of 10, that has to be increasing by the same one, the same distance, y is also increasing by a multiple of 2.5. So yes, it does display exponential behavior. And in fact, if you write to the equation of this, somewhere in there you would see 5/2 to the x power in your function, 5/2 being 2.5. Do a quick example again. Does this have exponential behavior? The first thing I'd check in my table of values is my x increasing by the same amount each time, because it needs to be over that same interval of x, whether every 1 or every 3, as it is in this case, does y increase the same exponential amount, the same multiple. So x is increasing by 3 each time, good. 480 to 120, that would be times 1/4. 120 to 30, times 1/4. 30 to 7.5, times 1/4. Yes, all three of those are the same. It's increasing at a set multiple. Therefore, yes, once again, this displays exponential behavior, and somewhere in this function you would see 1/4 to the x power. I say somewhere because there might be a number out front like that, 5 times 1/4 to the x power. Don't know for sure based on this simple analysis of it.